how to predict the products of double replacement reactions. And we're going to start by looking at that question from your practice packet that has this table in it. And the chemical substances that are on this table are reactants. And so it's asking you to write the products of each reaction in the boxes that correspond to the two reactants. And so for the first part, we're going to just predict what those two products are going to be. And then for the second part of the question, we're going to come down here and use these solubility rules to determine whether that is a substance that is still in an aqueous solution or whether it's precipitated out to form either a solid or a liquid. And so, like I said at the beginning, we're just going to be focusing on determining what these two products are. So for this first example, we're going to use silver nitrate and potassium bromide. And to start off, I'm going to come over here and I'm going to write out the equation for the reaction. So I have silver nitrate, and this is going to have to be an aqueous solution. Ionic substances have to be dissolved in something usually in order to react. So I'm going to put aqueous so that it indicates that that's dissolved in water. And then potassium bromide here. And then the goal of this, what we're trying to find are these two products right here. Okay, so these are our unknowns, and that's what we need to find. So the easiest way to start out doing this is to take each one of the chemical substances you have here and break it down into the ions that make up that substance. So for example, in this first one, silver nitrate, I have a silver ion and a nitrate ion. I know that nitrate has a -1 charge because I can look that up on my list of polyatomic ions, but silver is a transition metal, and so I need to be able to determine the charge on that. So I'm going to take a look at this compound up here, and I see that it's in a 1-to-1 ratio, which means there's one silver ion for every nitrate anion. So because those are in a 1-to-1 ratio and the charge on this is -1, silver is going to have to be equal and opposite in charge, so it's going to be +1. And then I need to do the same thing for potassium bromide. So potassium, we know that's in group 1, so that's going to be a +1 charge, and bromine is going to be -1. Okay? And now I've broken these down, and what I've actually done is I've kind of shown what happens to these substances when they are in water. So I'm going to draw a little picture here to show you what's happening in this aqueous solution, at least initially. So in this aqueous solution, I've got silver ions. So the blue represents the silver and the nitrate ions. I'm just going to kind of spread them out here. All right. And now I've got potassium bromide ions also in that same solution. So let's see, I've got a plus here and a minus here. All right, so here's my ionic solution that has both silver nitrate ions and potassium bromide ions dissolved in this water. And it's important to remember that with ionic substances, when they dissolve, remember their cations and anions dissociate from one another, meaning they move away from one another, and they're surrounded by water molecules. And it's the polarity of the water molecules that helps the water to surround these charged particles and keep them separated from one another. So now we've got water that has all these positive and negative charges spread out in solution. All right, so this is what it might look like. But we need to go a little farther to determine whether some of these are going to come together to form a new compound that's not soluble in water or not. So back to this over here. The next step that we want to do is we want to switch our positive charges. So this potassium is going to come over here and take silver's place, and silver is going to come over here and take potassium's place. So then we end up with the following. We get potassium with a +1 charge, and nitrate with a -1 charge, and then silver with a +1, and bromine with a -1. Oops, I forgot my R. Okay, so now we can see how these can start to form 2 new compounds. And the next thing that we want to do is we just want to balance our chemical formulas here. We just want to make sure that the formulas are written correctly. And normally, remember, this is the point where we would crisscross our charges. But in the case of both of these compounds, both charges are equal and opposite, so they just basically cancel each other out. So I'm going to write this compound as potassium nitrate, KNO3, and then I'll end up with silver bromide, like this. So there's my 2 products, and remember that those are the products of the 2 reactants up here. Okay, so now I'm going to go ahead and I'm just going to write out this whole formula again into one big chemical equation. So I've got AgNO3 aqueous plus potassium bromide aqueous, and that's going to yield, potassium nitrate and silver bromide. Now, what I need to do is I need to determine whether these products that I've come up with are soluble or not. And so we're going to use the solubility table for this second part. So our solubility table is this second table that's down here. And we're going to look at this first part right here. This first part is a list of ions that tend to form compounds that are usually soluble in water. So we always start off assuming that compounds containing these ions are soluble, but if you notice over in this second column up in the top half, it says common exceptions. And so down here at the bottom, 4 of these ions have exceptions. And if it's an exception, it means that if any 4 of these ions, bromine, chlorine, iodine, or sulfate, are in compounds with these other ions that are listed as exceptions, then they're no longer going to be soluble in water. Okay? And if we take a look down here at the bottom table, and this bottom table is a list of ions whose compounds are typically not soluble in water. So they make more compounds that are not soluble in water, or their compounds are more often not soluble in water. Let's take a look at or make up an example here. So hydroxide, the OH group, when we have this hydroxide polyatomic ion, most compounds that contain this are not soluble in water, unless those compounds would be like ammonium hydroxide or a hydroxide of any of the alkali metal cations, so like maybe potassium hydroxide or sodium hydroxide. And then if you had calcium, strontium, or barium hydroxide, those would all be soluble in water because those are the exceptions for any compound containing hydroxide. So again, on the bottom, we always assume not soluble in water unless it meets one of these exceptions down here. Okay, so let's give this a try. And so now I've got potassium nitrate here. And one more thing that we want to notice about this table is that most of the ions listed on here are negatively charged or anions, except the ammonium ion. It's the only positively charged ion here. So when we're looking at these compounds, we want to take a look first at the anion. So nitrate is the anion here in this compound. So we're going to come over here and we're going to look and see if we can find nitrate. And nitrate just happens to be right here up at the top. It's under the column of ions whose compounds are normally soluble in water. And there are no exceptions, which means this substance right here would be aqueous. We would write aqueous next to that. And so now let's take a look at this one right here. This is our anion right here, is bromine. So let's take a look here. And bromine is right here. And bromine is typically, its compounds are typically soluble in water, pretty easily dissolved in water. But we have to check because this is one of the 4 that has exceptions, and we see that silver is one of the exceptions, and so that means that this compound is not soluble in water, and this would form a solid, okay? And so there are, well, we'll talk about that in a minute. This compound right here, because it's solid, is formed. That means a reaction did take place, and this is a new substance that's being formed. Now, if you get a problem and both of your products end up being in aqueous form, that means that nothing has really happened. They're still kind of floating around up here. No reaction has taken place. But when we got this solid like this, that means these positive bromines right here are teaming up or pairing up with our negatively charged bromines. They're coming together and forming this solid. So all of these circles that I'm drawing around here are solid particles that are forming between silver and bromine, okay? So those are coming out of solution to form a solid particle that will eventually could eventually settle at the bottom of this solution. And all of these other ions that are left in here, they're not reacting with each other, they're just staying dissolved in solution. So nothing's happening, okay? So if we had a situation where we had 2 aqueous products, then we would say that's no reaction. One other thing that you could see is that water would form as one of your products. And if water forms as one of your products, we know that water is a liquid itself at room temperature. And water does not really dissolve in itself, just water is water. So we would write, instead of S, we would write L for liquid. And then that would be the case for any other liquid that we might make. Water would be the most common one that we would see in our class. So if you have any questions, it'd be a good idea to go ahead and pause the video for a minute just to write those down in your notebook so that you can address them in class, or we can address them in class. But to finish up this video, I kind of want to just go through and give you guys some steps for, or some basic steps for solving another one of these problems on your own. So what you want to do, step 1 is to just write out your products. So step 1 is, or not your products, your reactants. Reactants. Okay. Step 2 is to break reactants down into ions that make them up. Okay, so we broke it down into ions. Step 3 would be to switch your positives. Or your cations, switch your cations. And then step 4 would be to balance the product formulas. And step 5 would be to determine the solubility of new products. And then you're done. All right, so remember, write down any questions you have so we can talk about it in class, and I'll see you guys then.